So this is something from Nat Geo that was put together just a few months after the earthquake. I think it was less than a year after. I really can't believe it's already been 10 years, but anyhow, here we go.
All across northern Japan, they felt it. A violent magnitude 9.0 earthquake on March 11, 2011. It was centered about 80 miles offshore, and tsunami warnings went up immediately. In coastal cities, people knew what to do next: run to higher ground. It's from these vantage points on hills and in tall buildings that incredible footage was captured. In Kesanuma, people retreated to a high-rise rooftop and could only watch in horror as tsunami waves inundated their city, knocking buildings into rubble and mixing into a kind of tsunami soup filled with vehicles, building parts, and contents. Seawater cascaded over sea walls and into cities. This video shows the water rushing over an 18-foot seawall in the Kamaishi city. The seawall here was the world's deepest and largest, but not enough for the magnitude of the March 11 disaster. It was the largest quake ever known in Japan, and one of the 5 largest recorded in the world. More than 28,000 people are confirmed dead or missing. When two tectonic plates...
He said 28,000. It was, I have to look at the date on this. The Guardian article says only 18,500. But between, collapsing buildings, but they're built pretty smart because they're used to earthquakes. They're on a fault, right? They're at the juncture of several plates. So the Pacific plate is on the east, and then they have their own little mini plates, and then the Eurasian plate's on their west, and then there's actually 2 plates in between Japan and the rest of Asia. But it's crazy.
Pushed together under the sea, the resulting earthquake sends an enormous burst of energy up through the ocean, displacing enormous quantities of water. With the upward motion, a series of waves expands in all directions. In deep water, these waves travel fast, up to 500 miles an hour, but only reach a height of a few feet. A passing ship might not even notice. But as the waves enter shallow waters, friction with the ocean floor lowers the wave's speed, but raises their height. This video is from a Japan Coast Guard ship confronting a tsunami wave in shallow water on March 11.
That would be so scary.
And a rare view from the air, video of a tsunami wave approaching the shoreline.
So one of the problems, so in 2004, there was a huge earthquake in Indonesia, and a lot of people from Europe go to Indonesia, like we go down to Mexico, whatever, Guadalajara, to go vacation. A lot of people from Europe go to Indonesia, and it was a Christmas holiday. Thousands of European tourists were there, and there's actually a story of a little girl. She was that little girl at that time. She was like 12. She realized what was happening. Everybody else goes, wow, look at the ocean going out, honey. Look, all the sand. I can walk all the way out into the ocean. So a lot of people walk out into the sand. Like, oh, what's going on? Because they didn't know. They're not used to. They don't get tsunamis in England, right? So anyway, this young girl had just been studying about tsunamis in her science class, in her 6th grade class. So yeah, probably 12. And she said, "Oh, that's a tsunami." And her family got up into a hotel, multi-story, and was okay. But pretty crazy. Anyhow, if you see the water going out like that at the beach, I mean, yeah, it goes a little ways on the tides, and sometimes we have king tides and all that other stuff, but just get to high ground, especially if you felt an earthquake, which you probably would have noticed first. Anyhow, so there'll be multiple waves. So we get tsunami warnings here on the West Coast because we're on fault lines too. And tsunamis can start. They actually were calling for, it could have reflected back to us in California all the way from Japan. It was only a few feet. It was nothing like it was here at the island, but it can be a really big deal. I can remember being in the Bay Area 6 years ago, I think, 5 or 6 years ago. And they had cordoned off, they had taped off the like the overlooks by the beach because they were afraid of a tsunami. There had been an earthquake and they had all the park people coming out and blocking people from getting close to the shore. It was only like a few inches, but it was a little bit of a rise, but nothing super dangerous. However, what a lot of people don't know is pretty much from Monterey Bay north into Oregon, there's been big tsunamis, not in recorded memory for a lot of people, especially in Oregon, Southern Oregon, but they actually have tsunami drills for the schools that are close to the shoreline, close to the coast in Oregon. They actually have tsunami drills for kids, like we do fire drills, okay? You just go uphill, you go up, you get a, you walk, where are you gonna walk? What's the path to get higher ground? So.
In Japan, some tsunami waves reach as far as 3 miles inland.
It's a long way.
Japan may be the most seismologically studied country in the world, and with more than 1,200 high-precision GPS stations, a geophysicist at the University of Alaska used the data to create a visualization of the March 11th quake.
Energy wave is coming through.
The waves of displacement that you see were moving as fast as 5 miles per second.
Who knew?
In this photo, the ripples of tsunami waves are seen moving upstream in the Naka River at Hitachinaka City. New technology left an enormous amount of visual evidence for study in years to come, and can perhaps help us better understand the power of earthquakes and tsunamis and prevent loss of life in the future.
So the state of California has developed the My Shake app, and with the I think UC and other scientists, but you can get that downloaded. We're not going to have a big earthquake in Sonora. Have you guys ever felt an earthquake in Sonora? Most of us have. Oh, okay, in other places. Anybody in Sonora? If you have a 2-story house, you'll probably be more likely to notice it, but most of them aren't super big. So, yeah, most of them aren't that big. So on the Richter scale, like a 2.5, some people will feel, but a 3 is starting to, you can feel it. 4 or 5, you definitely are feeling a 5. And then you start getting into the 6s and you start getting a lot of potential damage. The earthquakes that we usually feel here are coming from the east side. You know, this is a volcanically, used to be, right? There's lots of volcanic rock around here. And Mount Shasta and stuff, those are old volcanoes. I just didn't know. And so, you know, we're on the Pacific Plate. The juncture, you can actually see where the Pacific Plate and the North American, we're on the North American Plate still, excuse me. You can see where the Pacific Plate and North American Plate meet the, on the coastline, and then also the San Andreas Fault runs right along I-5. You can see it in Hollister area. That whole area is really, really earthquake active. We haven't had a super big earthquake in the state for a while. You know, we've had some decent sized ones, but the last really, you know, bad one was a 6.9 that was in 1989 in San Francisco. We're overdue for a big quake, which isn't super comforting, but you prepare for earthquake the same way you would prepare for a wildfire. Have an emergency plan, have water, have extra food, have batteries, have a way to charge your devices, although, you know, the power lines will probably be out.
Not sure where it was. Like 5 years ago, but we lived in Northeast. I remember like the
Yes. Yes, you can feel it. And what's weird though, that one I kind of remember, it was, I hurt, you know, it was like a boom, kind of weird. It was really strange, but that was coming from the east side too, not the coastal stuff. So, you know, we can have earthquakes if you're at the coastline lots of us go to the beach. Lots of us go to Santa Cruz in the Bay Area. If there's an earthquake, get the high ground. Okay. Not every earthquake creates a tsunami. It's a weird combination of events, and just be aware of it. So, and then look, these showed up yesterday. Oh my gosh. So glad I was home because it was pouring rain. My husband has started a burn pile, and I went out at my lunch break to go rake up the coals, and I hear this, I'm just screaming. I'm like, where are the goats? Are there? They think they're going to melt in the rain. They're all in the barn, and yet this thing is screaming, little tiny baby goat. She was all by herself. Mom had ditched her. She was inside with the brother under the barn. Anyway, so I scooped her up in a towel and dried her off. And everybody's fine. Everybody's fine. Maybe. So cute. Well, it's not unavailable. Come on. Just played it. What are you talking about? Anyway, they are loud. It's loud. Couldn't even quite see her out in the field. Huh? The twins, yeah. That's their brother and sister. So. She's so tiny. Yeah. Anyhow, they're very, very cute. And they're going to take them away. No. Take all my fun away. Sorry. Oh, well. It was fun while it lasted. There's a couple of more does that are supposed to kid, so maybe we'll see some more. Anyhow, baby goats, they're cheer everybody up. Sorry, I know it has nothing to do with chemistry. Thank you for indulging me. All right, what are we doing today? We're talking about our lab. Who still has bobby pins to heat up? Did this class get completely done? Oh, you lucky dogs. All right, so we're going to work on the conclusions. So I want to talk to you about what I expect in conclusions because we haven't done conclusions before. So those of you at home, I videotaped myself doing the lab on Tuesday afternoon. So that is in, Wi-Fi is really slow, sorry about that. That is here. For those of you that are at home, you don't need to listen to this, everybody. You can watch that and get your observations from what I did. I apologize that you can't do it with us. I'm going to talk about what I want to see in your conclusions, and that is at the end of the document. So if you scroll to that, if you haven't already. Okay, so I'm submitting it. It's not due today. The instructions are from when we used to do paper and pencil stuff. So doesn't that seem like forever ago? I'm just going to ask you to do it on this lab paper or make a separate Google Doc and then put it with your lab. So there's 3 parts. When I ask you to do a conclusion, I like it in 3 parts. And I'll just what I already used from earlier classes. There's 3 separate paragraphs. The paragraph should be offset. I should never see a big blob of writing, a whole page of solid writing. Okay, break it into pieces for me. First part is some background information. Okay, and basically, what did you do the lab for? What was the purpose? What did you expect if you are asked to do a hypothesis? I don't always do those. And then also make sure, since the purpose of this lab, way back at the front, to learn about alloys and metallic bonding and document the effect of heating and cooling treatments on the behavior of a common alloy and describe the changes at the atomic level, okay, how that behavior is, why it happened. So you're going to also need to tell the reader, you're going to assume that the reader doesn't know anything about metals and alloys. So you want to make sure that you tell the reader what an alloy is and what a metallic bond is. Okay, so if there's that purpose is kind of all smushed together. So make sure in that starting paragraph, you tell me what you're doing, why you're doing it, and give me clues about what you're investigating, okay? The second part, the main part of the conclusions, are your results. And in your results, you also give me a little bit about the procedures. Not a lot. I don't need to know that you got to your lab station and put on your goggles and got out your equipment and lit your burner and. Okay, just tell me what you're doing. And each one of these bobby pins had a different treatment. The first bobby pin didn't have anything. It was just an alloy, okay? So this alloy, there's an explanation. Don't just copy and paste my explanations. Put it into your own words to some degree, please. Okay, this one didn't have anything. It was springy because of the mixture of atoms in it. And then in the annealing part, remember you did a high heat treatment and you slow cool. So those are your independent variables. They're also called manipulated variables. These are the ones that you, the scientist, changed on purpose. You heated them differently, you cooled them differently, okay? And that gave them different responses. That's their behavior. So the dependent variable is the behavior of the bobby pin. How did its behavior change? You have the baseline of the first one that you didn't do anything to, and then things got different as you went through. Okay. All right, so make sure you put in little answers where the yellow boxes are too. And then the explanation for why high heat and slow cool makes it soft is in this box. And then the third bobby pin, you hardened it by heating it to a high temperature and cooling it fast. What happened when you tried to bend it? Why is that happening at the atomic level? Did I show this class, my babies? No? Okay, this is the class I forgot. So heating something makes the atoms move faster. Okay? So when you have a solid, all the atoms are going to line up. And if you're heating it, and you freeze it quickly, there's lots of imperfections. There's lots of gaps, and it's not very even. But if you let it cool slowly, the atoms have a chance, the cations have a chance to get organized and line up. There may be some deviations and stuff, but for the most part, all the BBs are able to slide over each other, okay? The BBs, the atoms, the cations. And if you cool it slow enough, you can get all of them all nice and lined up, and that's why it's soft, because there's nothing, it's not catching on anything as you're trying to bend it. Whereas if you just freeze it, it's all messed up and you can't bend it easily. It actually breaks. Good. All right. So that's what's in these little boxes explaining that. And then the last one, when you got it back to kind of some spring again, it's because it's in between super soft and in between super hard. It's got a little bit of give, but not a lot. And that's the springiness. So you can make a bobby pin springy for two reasons. Its composition, what elements are in there, and how you treated it. Okay, the heating and cooling. Jack, did you have a question?
So would it be considered springy or?
It should be springy. That's why it says the spring is back. That hopefully is what happened. So again, those are the 4 treatments. And so you can make 4 separate little paragraphs. They're not going to be perfect little, 5-sentence paragraphs. I don't need a big, just 2 or 3 statements for each one. Probably can cover it if you do it concisely. And then the last part, the 3rd paragraph. All right, so you got paragraph 1, paragraph 2, and then this one, sum it up. What could have gone wrong? What would you do differently if you got to do it again? Would you use a different metal? Would you use a bigger piece? I don't know. Okay, and then explain, just restate that heating and cooling can change the behavior of a metal, even as something as simple as a bobby pin, or I don't know. You guys are good writers. I'm sure you can figure something out. Okay. Your partner and you, your bobby pins that you put on paper, would you staple your two papers together if you did two separate sheets and drop them in the back, the staplers and the baskets in the back? And then do your conclusions here, or do it on a separate doc and put it in with the lab. Questions I can answer right now. If you want to work with your partner, totally fine. Just don't write exactly the same thing, okay? And so you're welcome to go back to your stations and talk through it with them, proofread each other's stuff, whatever you want to do, but don't have identical papers. You good? All right. And those of you at home, any questions? Yes, yes, yes.